Okay, I keep trying to get a perfect presentation, so I'm just going to roll with any mistakes I make this time, okay? Because I am running out of time. So here's my presentation. This is a model for predicting the motion of an object that we assume is moving at a constant velocity. Okay, so first we observe the motion of a real object, and we get the data out of it. Now you see a video here of a can which is rolled across the floor. I'm having some kind of a stubborn problem where the video now doesn't seem to play. Hope you will believe me that I did in fact extract this data. It is genuine. I assure you that it is. And we'll move on. So the first step then was to use this data to extract our initial conditions for the object in our model. So we're going to need the average velocity of the object, so we'll start with that. If we take the change in position over the first time step, and we divide it by the length of that time step, which you can see here, 0.033, then we will get the average velocity, and it gives us this number here. This we can use as the starting point of our model. So now that we've got all the initial conditions here that we got from our data, there's the initial position at time step 0, here's the velocity that we just calculated, the starting time is 0, and the length of each time step is 0.033, and that's because the video was taken at 30 frames per second. So now that we've got all that, we can get down to the physics. So while time is less than the length of our observed motion, 0.9, and you can see that correlation down here. Our observations end at 0.9. So we'll get to the physics. Now, Newton's law tells us that any object in motion will remain in motion unless it's acted upon by an external force. Since we know that we're studying constant velocity here, and our assumption is that the object's motion is at a constant velocity, we can safely assume then that all the net forces acting upon this object are 0. So we set that here, and then we get down to another thing that Newton's law tells us. It tells us that if we know the initial velocity of an object, the net forces that are acting on it, the mass of the object, and the amount of time that that force was acting, then we can extract the final velocity after the force has acted. And so we will do that here. Now, our force is always 0, which is always essentially going to yield the same number for velocity, which makes sense. Velocity is supposed to be constant, so the number should not be changing. Here we update the position of the ball with each time step with the new velocity that we calculate using Newton's second law, and then we update the time step. So getting all that, then we can produce data from our model, which we can compare with our observational data. We can look at that here in this spreadsheet. So the red line represents our model, and the blue dots represent our observed motion. You can see that there is a discrepancy that gets larger as time goes on. There could be a lot of reasons for this. If we had inaccurately tracked our motion in tracker, if there was motion along 2 planes instead of just one, if the camera were moving when the video was taken, any of these things could throw the data off. Now in this case, the reason that the data is actually off is because our assumptions were incorrect. We assumed that this object was moving at a constant velocity, which goes with the assumption that there are no net forces acting on that object. This is not true though. As the can rolls across the ground, there is a frictional force that acts upon the part of the can that's touching the ground. You can see at the beginning of the model here, the comparison, it looks like it's predicting it fairly accurately. It's moving fast, and the frictional force is fairly negligible, but it does build up over time to slow the object down. So you see that our model predicts that the object after the 0.9 seconds will move slightly farther than our observed data shows it actually moves. And that makes sense because the force of friction is slowing it down. So we have constructed a model that is fairly accurate. You can see why it's not completely accurate. If we were studying an object which was in fact moving at a constant velocity, then we would get data which was more closely correlated. Thank you for watching my presentation. Oh, I should mention also, this motion is along the x-axis. It's positive along the x-axis. That's just because that's what we labeled those axes in tracker. We could have labeled the axes y, x, giraffe, elephant, it wouldn't matter. It's just the way that we represent the data. If this had been the y-axis instead of the x-axis, we would simply be talking about motion along the y, but it still represents, in this case, horizontal motion. Thank you for watching my Lab 1 report.